Guys, we're going to take a look at number 24. And up until this point, dynamics with uniform circular motion and also kinematics with uniform circular motion has been, I'd say, a bit of a cakewalk. It's been easy because all we had to do was plug and chug. If we have the equations in front of us, we can do this. But at this point, we need to start looking at actual applications of this, okay, which requires you to not only know the formulas, be able to use the formulas, but also to be able to think in real life about the situation. Okay, so I'm going to just give you this is number 24, by the way, and I'm going to give you a situation which you've all experienced. And what this is, okay, is a swing set. Okay, and we'll say that this is the mass hanging from the end of the swing set. Okay, that's you. Okay, and we've all wanted to swing as high as we could get. And in fact, when I was real young, my friends would try to get me to go even higher. And you know what I really wanted to do was to go up and around and create a full circle and get full circular motion. I didn't do that, and there's a couple of friends of mine that when I was in elementary school, they tried to. They ended up getting up to like this point, and then they'd fall on their heads. Okay, at this point, so at that point, gravity was a bit greater than the tension in the string, and they ended up falling down. But that's the situation I want you to look at. Okay, now in number 24. Okay, it gives us a mass, okay, of 0.65 kilograms. Here it is. It gives us a radius of 0.5 meters. Now, this is not as big as a swing set, but it does illustrate the point. And at the bottom, the velocity, the bottom is 2.8 meters per second. Now, they're going to ask us a couple of things. Number one is to draw a free body diagram showing all the forces acting on this. Now, we can think of tension in the string as an opposing force to keep this here at that moment in time. So the tensional force has to be equal to some other force that's pulling down. Well, we know that just this object just sitting here, not moving, it's going to be mass times gravity. Okay, we know that. That's the weight. So we've got force number one is the weight. And then we've also got force number two, which is equivalent, okay, to we'll call this force 2, which is equivalent to the mass times the acceleration of the object. Okay, so this force 2 is equivalent to the mass times acceleration of the object. The object is accelerating. Okay, so the bottom of the string here, the bottom of our swing here, we are going to experience more tension or more apparent weight right here. Okay, so I just wanted you to get that, to kind of think about that in terms of like real life. Like, what did you feel at the bottom of this thing? You felt like you were heavier. Well, if you could have swung all the way up to the top, okay, you'd actually feel like you'd want to fall down and you'd feel lighter. Okay, so the first question we have, okay, is to draw a free body diagram for the ball when it's at the bottom of the circle. Well, here we go. Let's just rearrange this. So we've got this, we've got tension, which has to keep this ball here, having to equal these two forces. Our weight, and then the additional force due to the acceleration of the object. So the tension has to equal, we know the direction's opposite. Tension's going to pull up. It's going to be the opposite of mg plus ma. Okay, and then this, in the second question, it also asks us to set up the equations needed to determine the tension in the string. So, now here's the part where we have to really look at this visually. Because, because we already know that gravity is pulling down, okay, we know that the acceleration here, okay, is a positive acceleration. So this is where it presents a couple of issues for us. So let's just figure this out. T equals mass times gravity mass times gravity plus mass times acceleration. Okay, now we are not given an acceleration yet. We're only given a velocity, a radius, and a mass. So it looks like, guys, the next step we have to do is find that acceleration. Okay, so if A is v squared over r, okay, we can calculate that acceleration and plug it in here. So acceleration, 2.8 squared over the radius. We can find that. And in doing the calculations, I ended up with 15.7 meters per second squared. So that number has to be put into our acceleration. So let's clean this up a little bit. Tension in the string, 0.65. Let's actually do this out. So 0.65. The weight is 6.37 newtons. The acceleration times the mass, okay, would be 0.65 times 15.7 meters per second squared. So let's take a look at it. So that would be plus 10.2 newtons. So now what we've got is a situation where we're adding this, and we're calling it this. Okay, we're making these two equivalent. But notice we have a problem here. Okay, our problem is that we used what we know of as gravity being negative 9.8 meters per second squared. So I'm gonna add in a little exception, a little rule here, which allows us to use gravity in a way that'll be able to calculate tension. So if we take the absolute value of gravity, okay, then we can come up with a reasonable formula to calculate the tension. So mass times the absolute value of gravity plus ma, okay, equals our answer. So if this was an absolute value, it would be positive, and this would be positive as well. So the tension in the string, because we've got gravity working and we've also got acceleration of the object working, is going to be these two added up. Okay, the tension in the string is 16.6 newtons. Okay, now that is an exception to our rule for gravity. So if you were to use this formula, okay, for anything downward, it would work for finding the tension. Okay, so it's T equals mass times the absolute value of gravity plus mass times the acceleration. You'll end up with an answer as far as that goes. Okay, so the tension in the string is 16.6 newtons. I would actually go as far as saying the weight apparent is 16.6 newtons. Tension pulls up, weight pulls down. Okay, there you go. All right, so let's look at another problem shortly. That one was a lengthy problem, but it was very important for you to really understand like the actual physicality of the situation.